Very good evening, everyone. I'm audible to you.
Okay, so did anyone tried by themselves the insertion or the searching function in a tree? Okay, was it working fine? Okay, that's great. What about the deletion function? Did you started doing that? Okay, how many of you were successful doing the deletion? No, sorry. Okay. Okay, no worries. Who didn't it? For 0 and 1 node, it worked. And for 2 nodes, was it not working? Okay, got it. So I'll just start with the code. Just a minute. Just give me a minute. Okay, so we will start with the 0 node, then 1 node, and then finally we'll proceed towards the 2 node thing. Anyone who is having the confusion, okay, I have already written the function for answer. Node, delete, and you will be having the root node and the number which like the number on the node which you need to delete. Correct. I'll take it as a K. So what is the first thing that you need to check? Can you tell me how to start this function with? Okay, understood. Like if root is null, you know that you need not, you just need to return the root itself, right? So if root at any point is equal null, you need to return the root. Correct. After this, you need to check if your data is present either on the left hand side or on the right hand side, right? So you will check if root.data, let's suppose, or Let me write this condition in the opposite way. If k is less than root dot data, in that case, what we need to do? Then we have to move towards the left hand side to delete our node. Okay, so delete, you will call, sorry, my bad. You will write here root dot left. Yeah, and I want to ask why this function has node as its return type. Can anyone tell me that?
For recursion,
For recursion, no. In case, like let's suppose most of the cases you will be given the number which is not the root. Okay. In that case, obviously at the end you will be returning your root node and that is justified. Are you getting this?
no, once again, madam.
Yeah, say. See, what I'm trying to explain you here is, in any case, you have this tree. Okay, you are deleting this, still your root will be the same. You are deleting this, still your root is gonna be the same. But in case someone asks you to delete the root itself, then in that case, you should know which is your new root now. Okay, and for that purpose only, we are having node as our return type. Clear? Everyone else in the class, are you clear with this? Okay, I'll just move ahead. I can't see any one of your doubt. Again, we will call our delete function. We will be calling here root dot left, comma, the k will also be transferred. Clear, guys? Otherwise, you know that else condition, else if k is greater than root dot data. Yeah, right? In that case, you have to move towards the right. So root dot right is equals to, you need to call your delete function. You will be calling here root dot right and k will be transferred along with that. Clear? In case it is equal, you need to delete it from there itself, right? So here in the else block, you will check. You know that if k is less than root dot data, you move to the left. If k is greater than root dot data, you move to the right. But if that is the data itself, then you need to delete it, right? So now comes our main logic here. That is, we have to check if it has zero child nodes, or it has one child node, or it has two child nodes. Everyone, are you able to follow me? Yeah. So first of all, I will start with my basic condition. That is, it is a leaf node. So for it to be a leaf node, your root dot left here should be equals to null, as well as your root dot right should be equals to null. Okay, so if it is a leaf node, what we need to do? Return the node. That is, return the, you need to return null now. Yes. Else if you need to check either root dot left is not equals to null, or root dot right is not equals to null, correct? But better taking both of them together, it will be better. You take root dot left not equals to null, then what you need to return here? Why root dot left? Okay, let me tell you this enough here. I want to delete this particular node. Okay, if I want to delete this, I should point this node with this node. Yeah, we need to return this child node. Okay, got it. Next, else if again, same thing. I'm not gonna write the condition, just instead of root dot left, it's gonna be root dot right. Can return here, root dot right. Now coming to the else condition, what we decided in the else condition, either you can have minimum from the right hand side or maximum from the left hand side, right? So I will move to the maximum thing, move with the maximum thing. Else you need to proceed here. You will first of all find the maximum node. That is a separate function to find. Find max, you already know, yes or no? And here I will transfer root dot left. This function you can write. Then from here, I'll call again the delete function. Max will be now my current root. Okay, like for the current given tree root, max is gonna be my root, and I'm gonna, sorry, my bad. This should not be max dot data. Yeah, sorry. This should be max dot data. And can anyone tell me why I am writing this? Can anyone tell me why have I written this statement? Guys, I'm not able to hear you.
No, ma'am, not clear.
Okay. Correct. See, Vishnu, what we need to do, if we want to remove our current node and we want to replace it with our maximum node, then for that condition, we need to delete the maximum node, which is already existing in its current position.
Yeah, now
Yeah.
it's clear.
That's why we are like deleting the max, like we are passing the max node and we are deleting the max dot data. Clear?
Yes.
Okay, great. After this, it is done. You know that your current tree will be having max as its root. right? Clear now? Yes. So you can close this else block. So Kishan, you tried this, so you can tell me that did you follow it, and was your code the same? At the end, you have to return root. The last was different. Okay. Try to execute this code and you will get to know. And all these questions are there on HackerRank. By HackerRank, I don't mean to say that the normal, like the Ashok IT HackerRank questions, but I'm talking about the normal HackerRank questions. You go, you visit the tree section, and you will be getting like all the questions of trees over there, like the insertion function, deletion function, searching function, and all. Okay, perfect. So we were discussing level order traversal, right? And we have not still executed it.
So with this function, all like different levels of the tree, like first level or leaf or the two, whatever be the node, it will work. I was not very clear if it will take care of every condition.
That's why I'm asking to run it, right?
Okay, okay, I see.
Because my code can also have mistakes. If you guys will do it, you will let me know, then we will see now that what's the problem arising.
Yeah, okay. Now
Okay, and that will be a test for you guys, that were you awake in the class or were you sleeping in the class?
yeah, that's true.
Okay, so considering the level order, I just discussed 2Q approach and I tried to write it. But today we will discuss more approaches to level order traversal. I'll just quickly make. Guys, probably on Friday I won't be able to take the class, so I'm informing this in advance this time. And yeah, other than that, I'll be available on all the days. So yeah. Okay, so level order traversal. One thing which can be done is you need to print all the levels on a separate line. So you should know when you are switching from one level to another level, right? That is the main concern. Are you getting it? Yes. Okay. So that one day I was trying to like make you understand one of the approach of using single queue, but you guys were having little difficulty in that. Today we will try that. Okay. So we have to take a queue. Instead of drawing it, take a queue, and we have to push our root node into that. That is 7. Are you able to follow this? After 7, you know that, like, you have pushed a root node, and on the root node, there can't be other node on the same level, right? Root node means only a single node in that level. So as soon as you entered 7, you need to enter some kind of delimiter over here. Delimiter, you can say it as a bubble or something which will tell you that, okay, this level has been done. Are you guys getting it? After this, we will pop out this 7 and we will insert its respective children. That is 10 and 2. Are you guys getting it? Okay. Now delimiter is encountered. Okay. So we will just remove this delimiter and we will enter this delimiter over here. Clear? Again, we will pop out this 10. And now we are like, as soon as you get the delimiter, you have to change the line. So you printed 7, you got the delimiter, you change the line, and here came 10. As soon as you removed 10, you will insert its respective children, that is -6. Okay. Then you will remove 2. Since delimiter is still not found, you will still print 2 over here and enter its children, 15 and 2. Now the delimiter is encountered, so you have to change the line. Everyone, are you able to get this? Okay, so then again we'll keep doing the same. -6 I will remove. Okay, sorry. First I'll remove the delimiter.
Once again, I'm not following. Instead of 2, it should be 9 now, because -6, 15, 9 is the second level.
Oh, my bad. I placed 2.
Okay. And also I'm not following one thing is initially we are pushing everything and then we are popping it one by one, or at the time of pushing we are pushing the delimiter also.
See, we pushed a root node. Okay.
Yes.
Then we will be checking if our queue is empty or not. If the queue is not empty, then we will pop our number. Okay. So we popped out 7. Again, we will be checking if the queue is empty or not. So again, we will get a delimiter. Sorry, when we popped out 7, I pushed 10 and 2. Okay. The next time when it will check the queue is empty or not, again, it will find a delimiter. As soon as you find a delimiter, you know that you have to change the line in the printing statement.
Yeah. Oh, 1 second, one step back. While populating queue, like we are considering how many children are there. Like how are we populating queue?
We just started from a basic root node. That's it.
Okay. Okay.
I just entered one number at that time. That's it.
Okay.
Following?
Yeah.
Okay. You can think, you can ask your doubt. I'm giving you a minute.
So when I started with the root, then we are checking if there are any, I mean, so 10 and 2, before 10 and 2, we have to put the delimiter.
Like
If,
as soon as you entered the root node, okay,
yeah,
you push
we
the
put,
children's, you know that this level is ended, you have to place the delimiter.
okay.
Like basically, yeah, okay, you can consider it in that way. Doubts?
So, I mean, the delimiter is not a number. Let's say we are putting semicolon.
You can do that. But you have to make then it's a queue of characters or queue of strings. That's it.
Okay.
Clear? Sorry, Vishnu, I'm not getting a response.
I'm still like a little bit doubtful. I mean, I'm not practicing,
Okay.
but
Try to tell me your doubt. I'll try to resolve it.
so my doubt is like how, it's fine. Like what you're doing was correct. Only thing is that how do I know that
The
there are,
level has changed.
yeah, level has changed. Yeah. Yeah.
For the first thing, it's very clear. You entered your root node, you know that root node only has one number. That's it. Can you have multiple root nodes? No.
No.
After that, you have to place your delimiter over here, correct?
By default. Yeah.
Then you will check that whether your queue is empty or not. It is not empty, you will pop this.
Yeah.
While popping it, you have to populate its right node and the left node. So I populated 10 and 2. Clear?
Okay.
Then
Okay.
again, when you will check if queue is empty or not, you will get this delimiter. Since you know if delimiter has come, you need to change the line. Able to follow? So you will change the line now.
Yeah.
This will also pop out. After that, you will again check if the queue is empty or not.
Yeah.
So one thing more which you need to notice here, that you got the delimiter here, you changed your line, at the same time you place the delimiter at the end of the queue.
Yeah.
Getting it?
Yeah.
Like it's like basically you're blocking that level. Clear?
Got it.
So now you will again check, you will get 10, you will print it, you will get 2. Sorry, you got 10, print it and populate its children. You got 2, print it, populate its children, that is 15 and 9. Clear till now?
I have one doubt here. Like in order to go toward the 9, 6 and mine, I am in the like 10th node, and I can just check dot right or dot left, and then I find it -6 is there.
Yeah.
Then I have to traverse to 2 as the next node. So again, I have to do back and then right
See, you
and then.
need not think that much. That particular thing is being handled. You just need to focus on the next node you're going. Why are you going till here?
Oh, no, no, no. So I'm thinking that when you are putting 15,
Hmm.
in order to go to 15, I have to backtrack to
No,
level
no,
back.
no, no backtrack. It's just like you focused on 10, you got -6, your role is over here. Okay.
Correct. Yeah.
After that, you already have 2 in your queue. You're not backtracking or something. You have that node in your queue. Okay. So you will exactly reach that location via the node address. You will see if the left node and right node are there. If there, you will push it to the queue. That's it.
Okay, now I understand. Yeah.
Clear? So this is how the things are going. I'll just quickly finish it up. Delimiter removed. Delimiter will come here. -6 removed. Its respective children 2 will come. Yeah. Thanks, Kishan. So -6 will come here. Then 15. No children. Sorry. With -6, we have 2 children, 2 and 4. 15, no children. 9, no children. Just popped and printed. Okay. After that, it encountered delimiter. Again, delimiter will be placed here. With 2, it will enter, it will pop 2, print 2 on the next line, and it will insert the children 3 and 5. Then it will pop 4, it will print 4 and insert its respective children 12 and -8. Then again here the delimiter will come. The delimiter came, you will have to insert it over here. Then you need to pop all these elements, print it here. And when all removed, this delimiter will also be popped out. Queue is empty and you are done with your level order traversal. Clear, guys? So I can write a pseudo code for this now because we are good with our insertion and all. So we can write our first code in the trees completely. And the other one, which I told you guys, that every time you're going to, like other approach can be, every time you're going to a new level, just maintain a count variable or a level variable. So you're going to a next level, keep on increasing it, and you will know that when you have changed your level. Are you guys getting it? So I'm not gonna tell the entire approach in here, but I guess you guys can try that.
So, I mean, whenever we go from next, whenever we do next, then we increment the counter.
Correct.
Okay. Yeah, got it.
Got it? Okay. So I'll just, per level, we can maintain a counter. Yeah, right. That's exactly what I tried to say. Forgot to share my screen. Okay, quickly, can anyone tell me how, tell me the insertion function? Yeah, please tell me. I'll just write here root before this and initialize it and yep, here you can check if root is equal null. You need to return new node of x, right? Else you need to check if x is less than root dot data. In that case, you need to move to the left. So basically, it's gonna be root dot left is equals to insert. And here you're gonna call root dot left, comma k, sorry, x. Why is it? Okay, fine. I'm not sure why is it giving the error, but we'll just figure it out, I guess. Okay, I'll just wait here. Yeah, I guess this is fine. Okay, I'll try that as well. I tried that this static as well. It was not. No, actually, the error is not gone. We have another node class. So probably.
Ma'am, just put it like L node or something, Q node, in the
No,
class
no, I
name.
guess it's fine now. So we have our insertion, and now we'll focus on the level order traversal. I'll just take one queue. And here I'll just write q dot add root, and here I'll write q dot. Okay, you are taking what delimiter you are going to use over here. Okay,
Ma'am,
max value. Yeah.
any colon or oh, okay, yeah.
See, you have to take some data over here because if we want node address, okay. So I'm just adding here a delimiter while q dot size is not equals to 0. I'll just remove all of it. Okay. Then you will have to pop here. So int k equals to q dot poll. Okay. Have you tested it, Kishan? Poll, I guess it's not gonna work, but I'll just do it. Okay. Dot data. But before that, I need to insert it, right? So Kishan, okay. You can check also if it is a delimiter initially. So if q dot element dot data is equal integer dot max value. In that case, you need to pop it. So you will write here q dot remove, and you need to change the line. Okay, so then if it is left, then add it. At the end, you just need to q dot remove. Yeah, before that, I need to print the data. So sys out. Here I'll write q dot element dot data plus space. I guess whatever we discussed, I have written I have covered all the points over here. So we'll just check it. Is there any error here? What is the issue? Oops, it's not changing the line after 7. Okay, because we are not inserting it also. So here I need to if q dot size is greater than 1, so it's greater than 0, then in that case you need to add the delimiter. There is an exception. Thirteen 42. Okay, it is printing 2, 10, then minus 6, 4, 9, and 15, and then I guess it is printing all the required numbers. 1, 2, 3. I think the remote is going to be done. Kishan, I'm not getting your observation. Can you explain it? It is printing properly, but it is giving an exception. Let's just debug it. First of all, you try to make the binary tree of this particular data and then tell me if the result is right or not. So try to make it manually and tell me if we are getting the right answer or not. Okay, that is the task of you guys. Okay, so 7 is getting printed. Then after 7, 2 is getting inserted. Inside 2, I guess -6 and a -8. 4 are getting inserted. Sorry, -6 is there. 8 is on -8 on the right hand side. Okay, size is 2. Yes, size returned is 3. Okay, now size is 2. I cannot see all the data also getting printed. Yes. 7 to 10 are printed, -6, 4, 9, and 15 are printed. But 2 here is missing. And then 3, 5, 12, and -8 are printing. But this 2 is not getting printed. Yeah, sure, we can see the insert function again. It's better we can write a size here, size function. And I'll just size and root. See, it's 11. And I've taken, okay, let it be. Okay, it is not able to handle the duplicates. And that's the reason why the other two was not getting printed. And that's perfectly adjustable. Then Java 15, 51. Okay, so okay, I got it. What is the problem? Now it will print fine. Yeah. The thing was that when it was checking q dot size is greater than 0 or not, if it is not greater than 0, it is equals to 0. So it was like nothing it was doing in this if condition, but it was straightforwardly moving into this if condition. And here we have the if condition as q dot element dot left is not equals to null. So when there is nothing in the queue and it was trying to get q dot element, that's why it is throwing the error as no such element. Clear? And regarding the duplicate 2, which was not getting printed, I'll just add it again. Okay, and I'll just handle it in the insertion. That is, if x is greater than or equals to root dot data, then it should be inserted on the right hand side. Now it will print fine, I guess. Yeah, see. 2 is there, no? Yeah. Clear, everyone? Okay, so I guess there is no doubts in the level order traversal now. I have explained you 3 approaches. I have demonstrated you one of them in front of you. So I guess level order is done now. Clear, guys? Okay, then. So I guess yep.
I'm putting the code.
Yeah, code I'll share. And next, what I'll say, remaining will continue tomorrow. Oh, thank you for reminding that. Linked list problem, I'll just explain it today itself. Just a minute, I'll just share the code. Okay, I'll show the screen again. Okay, so for breaking the loop, what we were doing, we have a linked list. Okay, so let's suppose our S and I am like right now taking S and F are meeting at this point. Okay, so when they are meeting, we know that intersection exists. I'm taking this point as M. Clear? The length of the loop, I'm taking it as N. And the distance from the point of intersection from here to where S and F intersected, I am taking the distance as K. Clear with the terminologies?
So what is N?
N is the entire length of the loop.
Okay. M is where they meet. K is the difference between the starting and the
Correct.
middle.
Correct.
Yeah.
So just a minute. Just a minute, I guess. I guess M is not the point of intersection. It is taking the explanation. It is taking this length covered by S is from here to here it is M. The distance it needs to cover is to be K. So the total length which S needs to cover to complete this entire loop is going to be M plus K. Are you guys getting it?
There are three Ashok IT. Which one are you in? First, second, or third? Because I'm getting message. No good. I'm sending message. It's not going to you.
Okay. Actually, I'm the co-host, and yeah, there are two co-hosts as well. But I can't decide that one. You can try. The second one you can message. Vishnu, did you get it?
What? Yes, I'm clear. I'm
No,
just saying.
actually, you were asking now where to message. I was waiting for that.
Oh, okay. I'm saying hi. Did it reach you or no?
No,
Okay.
try another co-host.
Mm,
Yeah, I'm getting it now.
okay.
Guys, I am having the explanation, but I guess that is not a clear one, which is gonna tell. So, like, which is gonna actually explain it. So I'll just see that. Until then, if you want to try that, try this particular intersection thing, what you can do, wherever you are meeting your slow and fast pointer, from that point, you break it. Okay. So I'm breaking it at this point. So what will happen? Your linked list is going to look like this will be a straight chain here. And now this will be an additional one, right? And here you already know your, like you can have your pointer over here, head 2. You can have your pointer here, head 1. So you can simply start traversing from here. Just a minute. Basically look like this. So it's basically intersection of two linked lists that we have solved. Yes or no? So you can find its intersection point. You will know that like where it is intersecting. So from that point, you have to remove it. So you need to delink this. You will be having a node over here. And one more thing, like whatever nodes here you are getting freed, then you need to connect it back to the back. Is it clear? Is it clear to everyone? Because this explanation is gonna be little, I will say like what uh, I was trying to explain here is that slow is equals to m plus k. Your fast pointer is gonna be, it's better, just give me a minute. I'll try to explain it one time. If it's not like getting properly to you, then you just follow the next. So slow and fast I'll start, and then 1, 1, 2, 3, 3, 5. At 7, it is meeting. Your slow pointer is going to be here. Okay. So we were taking this length as K, and we were taking this length as M. Okay. And the entire length as N. I'm going to start my head from here. So initially my head pointer is at 1. My slow pointer is at 7. Next time they are going to move to 2, it is going to move to 8, it is going to move to 3, it is going to move to 9, and at the end it is going to move to 4, and here it is going to move to 9. So what I can explain you here out of this is somewhere when it, like wherever they are meeting M and K, like slow pointer and the fast pointer, somehow the distance, sorry, somehow the distance from the starting point till the intersection point and the distance from the slow points, like slow pointer and the intersection point, both are gonna be equals to K. Like this length and this length becomes equal. Okay. So to explain this, what they are like, what we take, we say here that overall if a slow pointer has to cover this entire loop, only we know that it is gonna cover once. Otherwise, it's like it's not even gonna finish this loop. Fast pointer, it can travel multiple times. So m plus k. The loop length is n. So it's gonna be Pn. Sorry, I guess I have used a wrong variable here. So m, remove this. M is gonna be the distance from this starting point till the wherever they meet. So that is m, and k is the distance that it has to travel to reach the intersection point. Okay. On the other hand, what we can say, the fast pointer, it travels m, it travels k, as well as there are chances it can rotate or you can revolve around the circle or the loop many times, right? So that's why I have taken it as Pn. Are you guys able to follow this? Okay. So just a minute. Yep. So there, what we say that fast pointer is equals to 2 times of the slow pointer. So fast pointer, I'll take it as m plus k plus 2 times, sorry, plus Pn is equals to 2 times of m plus k. So basically, you are going to get Pn is equals to m plus k. So are you guys able to follow what is happening? Okay, tell me. That m plus k is always going to be the multiple of that the number of times you are rounding in that circle, right? In the loop.
Yeah, ma'am, I'm agreeing with this, but there could be some number where this 2 times short pointer may be 3 or different number.
Why? Fast
Uh,
pointer is always moving 2 times ahead of the slow pointer. Why it will be 3 or 4?
because the starting point till the meeting point could be some unique number. It will
Vishnu, we
not.
are only talking about the relation between fast and slow pointer. That's it.
Okay, okay.
Are you getting it?
Yeah. Yeah, so between fast and slow pointer, yes, this 2 could be any another variable.
Again,
Something.
not clear.
Yeah. So okay, let's say the starting point is 3 away from the meeting point of the two of the circle cyclic. Okay, I'll come up with some numbers where this 2 may not match, or will it always match? See, if it is a complete cycle, like just cycle, then fast is equal to 2 times small will be okay. But there is one unknown part where the protruding part, which is common between the fast and small, is variable. Let's say the okay, I'll come up with a number and then ping on the
So, okay, I'll just conclude it at the end. So you can see that n is like m plus k is multiple of n. Okay. So basically you travel n plus k times in this loop. You try to travel m plus k times. You start from this point, travel for m plus k times. You are going to reach this particular point again, right? If it is a multiple, it's going to be.
correct.
So if you start your and if you are have already traveled these m nodes, so you are k short nodes, like you are short of k nodes to reach the intersection point.
Yeah.
Yeah. So basically it says that if you are k short, this means that sorry, like the way you move your slow and fast pointers, wherever you get the intersection, that is at slow and fast, and wherever your current head is, they are always k distance away from each other. Are you getting, like, it is placed in that way? If like, why I solved this particular like problem in front of you, why I identified slow and fast pointer intersection in front of you, I could have taken any random node and started the slow and fast pointer from there. But the thing is, they are placed in that manner, they meet at that point from where the head node and the slow pointer are at equal distance from each other. Are you guys able to follow it?
Yeah, that is fine. That is correct.
Okay, so this was the explanation. It was like something which at the end you understand, but it's like to the other person, you are not completely able to justify. But yeah, if you give this explanation to your interviewer, he or she will be satisfied. And other than that, you already have another solution as well. So you can try both of them now. Clear, guys? Okay, then. So now I'll just close the class and I'll see you guys tomorrow. Bye-bye. Good night.
Thank you.